Hello everybody, welcome to Unit 4 of the course on Embedded Systems Programming. What we are going to be looking at over here are some topics related to clocks and timing in the context of microcontrollers. So an outline, I'll be starting by talking about clocking in the context of microcontrollers, then talk a little bit about the concept of sampling, analog to digital conversion. A very interesting application that is very commonly used in the context of microcontrollers called PWM or pulse width modulation, and finally talk a little bit more detail about the general concept of how timers are used in microcontrollers, in particular for things like input capture and so on. So let's start by talking about clocking. The first thing we need to understand is what is a clock in the context of a digital circuit. So a generic digital circuit, right, and I'm assuming here that all of you are familiar with the basic components of digital circuits. You all know that there are combinational logic, things like AND gates, OR gates, NOT gates, NAND gates and so on, which are used in order to implement basic Boolean functions. Now the property of a combinational gate is that the output, which is either a 0 or a 1, it's a binary output or a Boolean output, is purely dependent on its inputs. It's just a combinational function of what the current inputs are. So if any one of the inputs changes, the output may or may not change, of course. So for example, if one of the inputs of an AND gate is 0, it doesn't matter what the other input does, whether it changes from 0 to 1 or not, the output is going to remain 0, right? So it's not that the output of a combinational gate has to change for every change in the inputs, but it is always a direct function of the inputs. In other words, if the inputs are known, the output is known as well. Now that's fine, except that we also have another kind of element in digital circuits, which are usually called the sequential elements, and these are used in order to maintain some notion of state or storage. Essentially what they allow you to do is to take a particular value and to store it for later use, right? And this brings about a very useful concept of retaining a state associated with a system. The state essentially says that this is the present state. I'm using the term sort of informally and loosely over here, so it's sort of a circular definition. I'm using the word state in order to define state, but there are more formal definitions possible, but what I want to try and do is just focus on the core concept here. So the idea of a state of a system is, this is the present set of all the values that you have. Something has been stored over here based on maybe prior computations or the prior history of what the system went through, and this part of it gets stored in elements called flip-flops or latches or registers, right? There are multiple terms used for that. Now in general, any digital circuit can be viewed in this fashion. You have a present state of the system. You also have certain other inputs, which is not explicitly shown over here, right? Now a combination of this present state and the inputs to the system goes through combinational logic and comes back as the next state. And in addition to this, so in other words, what we have over here is these are the inputs and you have this coming out as outputs. Of course, this could also, a portion of this could also be treated as the outputs of the system, right? The point being that just these two different kinds of circuit elements are sufficient to give rise to a very broad variety of different functionalities, and in particular all forms of computation that we are aware of today can be sort of encapsulated within this kind of logic, right? So what is the important point over here? Essentially the thing is that there is some notion of a sequential element that stores state, and the most important difference between this sequential element and the combinational element is that the state stored in the sequential element is dependent not just on the present inputs, but also on when, the time at which a particular signal called the clock had a transition or changed its value, right? So it is quite possible that the clock has a certain value, the inputs have certain values, but the output is dependent on what happened at the last time that the clock changed its value, and not on what the present value of the inputs are. That is a crucial difference between a sequential element and this combinational logic, where at any point in time, if I change one of the inputs, the output is always directly a function of what the present inputs are. Okay, so just to recap, the whole purpose of this system state is that it retains some kind of previous history of the circuit. It's a memory device, and therefore we can compute an output as a combination of the previous state or previously created state and the present inputs to the system. There are many terms that are used for these kind of circuit elements. You will come across things like flip-flop, register, latch. We are not concerning ourselves with how exactly the sequential element is going to be implemented. That you would have seen in the course on digital systems. There are multiple different elements, but what matters is that the most common among them is probably what's called the edge triggered flip-flop. So the majority of digital circuits today rely on edge triggered flip-flops. Now there are reasons for this, the primary reason being that edge triggered flip-flops make it easier for us to analyze the behavior of the circuit. In particular, there is a notion of critical paths and the critical timing that is associated, critical delay that is associated with the circuit elements, which is easiest to analyze when you are working with edge triggered flip-flops. That's why they are the most common, but they are not the only means by which you can retain state in a circuit. Once again, as purely an embedded systems designer, you probably don't even need to worry about the different kinds of such elements. All that you need to know at this point is that there is a signal called a clock, and how often that clock signal transitions is ultimately going to determine at what rate the outputs can change, and therefore at what rate the system can perform computations. So if I have a flip-flop like this or an edge triggered register, right, I'll use the terms interchangeably over here. Latch usually refers to something slightly different. It is what's called a level triggered latch. Having said that, there are contexts in which people just use all of those terms sort of interchangeably. What matters is that they are sequential elements. So as far as we are concerned, since we have decided to focus on edge triggered elements, we are looking at what's called a positive edge. A positive edge on a clock is something where the clock signal, which is after all a digital signal, and therefore we are going to assume it takes on two values, 0 VDD, 0 VDD, it can switch between those. Of course, it goes through all the values in between in the process of transition, but the 0 and VDD are the only relevant Boolean values or binary values that you care about. Now, when the clock transitions from 0 to 1, we consider that as a positive edge, and therefore we are interested in how many such positive edges occur per unit time in the system, because on each of those positive edges, this register allows some data to go through from input to output, and once it is at the output, it can then be used by the combinational logic for a new evaluation, which will in turn make its way back over here and update the state of the system. So intuitively, you can imagine that the more number of edges that you have, or the more such edges that you have per unit time, the more computation you can perform in the same amount of time. So a CPU in general, a processing unit, right, which is after all the core element of a microcontroller, can be thought of as some kind of a complex state machine, right? And what do I mean by a state machine? It is something that retains a state and then performs computations based on a combination of that present state and the current inputs. So in a CPU, the registers that are there in the CPU, as well as some parts of the control logic such as the program counter and so on, together constitute the present state of the system. And the instructions and any other inputs that are available to the system, that combined with this state will decide what computation actually happens. All this means that you need a clock in order to update these registers, and that ultimately is the clock that we are referring to when we talk about the speed of a processor, right? So in general, the speed of a clock is measured in terms of the number of cycles per second. The idea being that if I have, let's say, 1000 cycles per second, I can potentially perform 1000 computations in 1 second. Typical speeds, even for simple microcontrollers, are probably in the range of more than 1 megahertz, meaning more than 1 million cycles per second. and of course you probably have at least seen the numbers associated with the processors in your laptop or even your phone these days, which is upwards of 1 gigahertz, which means 10 to the power of 9 clock edges per second. Okay, so that is why computers appear fast, right? They're able to perform so many different computations per second that they can fool the human beings into thinking that they are doing multiple things all at the same time, right? Even though they might be doing them one after the other. Now, therefore, it seems obvious that having more cycles per second is a good thing. There are drawbacks which we will get to later. But then comes the question, why not keep increasing it? Why do I stop at 1 megahertz? Why do I stop at 1 gigahertz? Why not go to 10, 20, 100 or 1 terahertz, right? And the point is that at the end of the day, these logic gates that we are talking about are ultimately built out of physical elements. There are transistors, there are resistors, there are capacitors. As a result, it takes a finite amount of time for voltages to build up and discharge on each of these elements. That in turn translates into a delay through each gate. So the delay through the gates are completely determined by electrical characteristics of the system, right? And as a result, there are limits on how fast a system can work. Therefore, when you see that a particular processor works at 1 gigahertz, the reason is that the circuit elements that have been put together in there have a total delay through them, which basically limits the speed at which I can reliably clock this system to a time period of 1 nanosecond or a clock frequency of 1 gigahertz. If I try switching the clock faster than that, there may be computations which are not able to make their way through all the different levels of logic, and as a result I get the wrong results for whatever computation I'm trying to do. Okay. So the electrical characteristics which you would come across in the course on digital design are ultimately what determine the speed at which a given circuit can work. For now, all that we care about is there is a number associated with each clock, which is the number of cycles per second. On the face of it, the first guess would be that we would like that number to be as large as possible, and we would also like to understand what are the limitations. Why would we not want it to be as large as possible? So just to sort of summarize what we understand about clock speed, as you might imagine, the first thing is a desirable property of this seems to be that we would like it to be high speed, meaning more computations can be performed per second, right? After all, if more data can be sort of switched across the register, it means that more of that data can then run through that combinational logic, come back as a state update, and therefore everything works out well. Now obviously, every time I switch the clock, it then has to go through the combinational logic and come back before the next clock edge so that I can update the state in preparation for the next computation. That, as we said, is what determines the limit on the speed. Now, there are problems also associated with this, right? And the primary problem with having a high speed over here is that the more switching that you have, right, or the more times that any logic gate sort of switches up and down, it translates into more power being consumed by the system. We'll get to that again in a moment, right? There are also issues. For example, there are certain protocols such as the UART that we have already encountered, which are, by comparison to the CPU and such systems, slow protocols, right? As you might imagine, the typical operating speed of the UART is 9600 bits per second. It could go up more, but maybe up to around 100 kilobits per second. It's not really designed for much higher speeds than that. But the CPUs typically start at 1 megahertz and then start going up from there. So they're at least like 10 times faster than what the UART can do. So that becomes a question, right? I mean, how do I sort of balance these different clocks? By the time 1 bit or 1 byte has been transmitted, the CPU has probably performed a million or hundreds of instructions. Okay. Similarly, apart from the UART, there could be other peripherals with differing capabilities, right? So there could be high-speed peripherals such as Ethernet or cameras, where the speed might actually even be more than what the CPU is capable of handling. On the other end, there are low speed peripherals like keyboards or keypads, which are extremely slow, meaning that they typically operate on the order of like hundreds of milliseconds. Reason being that it's human interaction. It requires a human to actually press a key, which takes several tens to hundreds of milliseconds for meaningful interaction to occur. So both of these, all of these are essentially reasons why just going for raw speed may not always be the best option, right, when you are looking for the kind of operating speed of a microcontroller. But let's look a little bit more into this particular problem of power consumption, right. Now this is going to be a very sort of hand-wavy explanation. I am not getting into the details of what is happening over here, because in order to really understand what happens at this point, you need to get into how logic gates are implemented at a transistor level, and that's out of the scope of what we are doing in this course, right. But what I do want to convey is that there are certain characteristics that you need to keep in mind, which will help you in terms of understanding what could make a circuit consume more power, or what can be done to make it consume less power. So at a very sort of broad level, you can think of a gate in a digital circuit. The simplest gate is of course the inverter, the NOT gate. I provide an input, the output is basically the inverted form of that input, right. So for example, if the input goes from 0 to 1 and then goes back to 0 after some time, I would see that the output starts off high, it goes low when the input goes high, and then goes back high when the input goes low, right. Now what I am saying over here is this is an electrical signal, it's a voltage switching between 0 to VDD. This gate is in turn made up of some kinds of transistors which are configured as switches and so on. In turn, this output of this gate is connected to some other logic, right. But from an electrical point of view, I don't really care what that logic is. What matters is that it looks to me like a capacitance, right. And what that means is I can either have a 0 voltage on this capacitance, meaning that there is no charge stored in the capacitance and there is no current flowing through it, or this voltage over here goes high to VDD. I still have no current flowing through this, because that is how the gates are constructed, right. I don't have a static current flowing through this. So unless there is a very minor form of leakage current, as a first approximation, I can basically assume that there is no current and therefore this is just a capacitance. Now what that means is I have a capacitance and the voltage over here has been charged up to VDD, the supply voltage, because after all that's what corresponds to a logic 1. Now from physics, you know that what's going to happen over here is when a capacitor has a voltage across it, it means there is charge stored on the capacitance, and equivalently we can also infer that there is a certain amount of energy stored on this capacitor, and the magnitude of that energy is half CV squared, right. That's just from physics. What does that mean? It basically means that initially I had 0 charge over here, 0 energy stored on the capacitor, but after switching this gate, somehow some VDD amount of voltage, meaning that C into VDD amount of charge and therefore half CV squared of energy got deposited on this capacitor. How did that happen? Some current must have flowed from the supply voltage into the capacitor, causing it to charge. Now on the other hand, when the output sort of falls, goes low, whatever voltage was over here has to discharge, means that some current flows through the capacitor. It's a dynamic current, right. Some C dV by dt is going to happen and therefore there will be a current flowing through. It will cause this capacitor to discharge, which means that I have a source over here VDD. It provides some charge which then gets discharged later to ground. In both of these processes, it is passing through some circuit elements, and those circuit elements in turn are dissipative. They end up burning energy. They are basically dissipating some kind of energy over there. The long and short of it is, in one sort of up and down transition of the input and therefore of the output as well, a good approximation is to say that a total amount of energy equal to CV squared gets pulled out of the source and dissipated as heat essentially in this circuit, okay. In turn, what that means is if my output is somehow switching at some high frequency because the input was changing and therefore the output also kept changing at some speed, I can infer that the power that is the energy being dissipated per unit amount of time, is going to be proportional, right? Not exactly equal, it's proportional because there are a couple of other factors at play over here, to this capacitance, the square of the voltage into the switching frequency, the rate at which this output is switching. Okay. Now, let's look at this equation a little carefully. What it says is there are multiple components that determine the power being consumed in a circuit. One of them is F, which is the operating frequency, or more accurately the rate at which this particular element is switching. Okay, switching back and forth, 0 to 1 and then back to 0, right? One full cycle is the number of such full cycles per second is basically what we are looking at in terms of F. V is the supply voltage, because after all I am pulling it up to VDD and then discharging it back down to ground. So V squared. It's interesting, what it tells you is that a 5 volt supply is probably going to consume 4 times the power of a 2.45 volt supply, right? So it's not just double the power, it's 4 times, because there's a quadratic term over there. So voltage can actually have a very strong effect in terms of the total power being consumed by a circuit. And lastly, this C that I have talked about over here is just one particular capacitance, which is the load on this particular gate. In reality, it is all the gates that are present in my circuit. Each and every one of them is connected to some load, which in turn looks like a capacitance. So effectively I need to add up the capacitances across the entire system, meaning that a large circuit with a large number of gates, right, will essentially consume more power. So intuitively, in other words, at a very high abstract level, the faster that a circuit switches, the more power it's going to consume. The higher the voltage at which it's operating, the more power it will consume, and not just that, in a quadratic fashion. And finally, the larger the circuit, the more gates it has, the more power will be consumed. So all of these are sort of, they are giving you clues already about what you need to do if you want to build a low power system, a low power circuit, right? So you could play around with this equation and say that, hey, if I reduce the operating frequency, I can actually bring down the power. Similarly, if I use a smaller circuit, it will consume less power than a larger circuit that does the same work, right? What that means is that a simpler microcontroller with less gates and less logic will consume less power in general than a more complex and possibly more powerful processor that is doing the same task. Right? And finally, if I can operate things at low voltages, I can really win. I can get a huge improvement in the power, right? So clearly this tells us that operating at high speeds has a drawback. Yes, I can perform computations fast, but it can potentially be problematic as well. But the question you might ask is, okay, why not just keep reducing V, right? And it turns out that reducing V causes problems. It means that my transistors can no longer deliver current fast enough, they can't switch fast enough, and that in turn brings down the frequency at which I can operate. It ends up slowing the whole system down very dramatically, and I most likely won't be able to perform my computations on time if I reduce V too much. Okay, so these are some aspects that will keep coming up at various points when we talk about what we can do to reduce the power consumption in a circuit. Alright, with all of that background in terms of what are the desirable aspects of a clock, let's look specifically at the context of a microcontroller and what are the different kinds of clocks that are present over there. So the first thing that you will realize when you start reading data sheets for microcontrollers is that they typically have multiple clocks, right? And the natural question to be asked at that point is why? Because after all, if I have one single clock, right, I should be able to connect that to every flip-flop. And if I don't want to perform a computation, maybe just don't make it transition or don't use it at that point, or design my circuit such that it does the work and afterwards maybe sits idle or does something else, right? But it turns out that you get a lot of flexibility, especially in terms of trading off performance for power. You can actually selectively run different parts of the circuit at different speeds, right, if you have multiple clocks available in the system. So that's why this is considered a useful thing to have and is actually made use of while building complicated embedded systems. It allows you actually to partially shut down parts of the system. So you might have a microcontroller where perhaps for your particular application the entire communication subsystem, the I2C and SPI buses and so on, are not going to be used. The good thing is you can just shut off the clock, and in fact you can even shut off power to those parts of the system and thereby save on power, right? Remember that power only gets dissipated when there is actual transitions on the gates. So if I shut off the clock, make f equal to 0, presumably I should be able to save some amount of power. There is also something else called a real-time clock, which has a number of other useful applications. In particular, there are applications where you can put pretty much the whole microcontroller to sleep, except for this one slow clock which is almost at the hertz level, right? It's operating at a very low frequency compared to what the microcontroller would normally work at, right? But it can instantaneously, or very quickly rather, wake up the entire microcontroller and get it back into a functional state. So just by having this one alone, for example, you could trigger it to do things like maybe wake up once every few seconds, do some work and then go back into deep sleep. The rest of the microcontroller will just be completely asleep. The real-time clock alone will take care of waking the system up, getting it to do some work, and then finally the system can go back to sleep and wait for the next tick from the real-time clock. So it looks like there are some benefits to be gained from this, and knowing how to control the clocks in a system can play an important part in efficient design of an embedded platform. So let's quickly look at some of the clocks that are present in such systems. One of them is of course the sys clock, the system clock, which is fed to the CPU core, right? Typically this is the highest speed clock in the system because you want to have the maximum processing power. Occasionally you might end up with scenarios where either a camera or a high speed peripheral like Ethernet could potentially require a higher clock than what is actually being used in the CPU, but for the most part that's unlikely because the CPU still needs to be able to process the data coming from those peripherals at some level, right? So it's very rare to find a scenario where the CPU clock is actually significantly less than some other part of the system. Now, apart from the CPU, you typically have a large number of peripherals associated with a microcontroller. After all, that's what a microcontroller is, right? It includes the CPU and peripherals. And in a lot of cases, you want to have separate clocks for those peripherals. Why? Because you might have a peripheral like the UART, or you might have analog to digital converters that we will talk about later. And these might actually not need to operate at the same speed as your CPU. Right? As we will see later for the STM32 microcontrollers, for example, the CPU core typically works at 48 megahertz or some frequency around that. The UART, as we know, is less than 1 megahertz, right? And ADCs could possibly go up to 1 or a small number of megahertz, but unlikely to operate at speeds like 48 megahertz. You are not expected to operate at those speeds. So why give them such a high clock? Because after all, as we know, that high clocks will also result in higher power dissipation. So instead what is done is you actually derive different peripheral clocks that are fed to those parts of the systems and can just be used to trigger them in some sort of close to optimal fashion. Then there is the RTC, right, the real-time clock. As I already mentioned, this is extremely low speed compared to the system clock. Typically this would be in the tens of megahertz range. This RTC would be in the kilohertz range. A common speed is 32 kilohertz, right? Which also means presumably that it is low power, but it's low power for two reasons. One is that it's a slow clock, but the important thing is it's actually not used for performing computation as such. All that the RTC does is increment a counter, right? And at certain intervals it can basically give a signal that wakes up the rest of the CPU to do some useful work. Right? So it does timekeeping. It allows you to operate even when the CPU is sleeping. So for example, if I want to sleep for 1 minute and then wake up, my CPU doesn't need to sit there and actually count. It can just say, no, I'm going to sleep, wake me up after 1 minute. And the RTC can count 60 seconds and send a signal to wake up the CPU at that point. So alarm and wake up is one of the most common functionalities that RTCs do. They can also be used for certain kinds of time stamping applications. So if you have events that are not sort of happening very often, the RTC just keeps track of time, and every time the event happens, you just basically look at what is the count on the RTC. The CPU wakes up, takes that count from the RTC, saves it somewhere, or sends it off to some other host that's collecting data, and then goes back to sleep. And that way you can do time stamping of events, right? Every time that the event occurs, the CPU wakes up, looks at the RTC counter, and figures out how much time has passed since the last invocation of this event or last occurrence of this event. So the RTC is typically found in pretty much all microcontroller systems, right, and has some very specific use cases. Now of course comes the question of where are these clocks coming from, right, because as we already saw, we have circuits, the digital circuits which are the gates and the flip-flops, but those are elements that just exist inside the circuit itself. The only other thing that's required for them to work is a power supply, right? Whereas over here we are talking about a signal that actually explicitly needs to toggle back and forth. It needs to go from 0 to 1, 1 to 0, 0 to 1, 1 to 0, and so on, right? So we would like it to look something like a square wave. Right? There are multiple ways of generating these signals. In the basic circuits course, you have probably already seen what oscillators look like, right? There are multiple ways of building oscillators. There are things called RC oscillators, which basically use a resistor and capacitor along with some kind of feedback element in order to create oscillations. There can be things using circuit elements called Schmitt triggers, right? All of these can be used in order to create a clock like signal, which is basically a square wave, right? And these RC oscillators are very often in fact built in to most microcontrollers, right? Now what that means is that if I just take a microcontroller chip, I can actually use it without even providing a separate clock, because it has its own internal notion of a clock, right, which is great. I mean, it reduces the number of parts that you need to build a system. The problem is RC oscillators in general are not very accurate, right? They are heavily dependent on the circuit temperature, the voltage supply, the environmental conditions, including things like humidity and so on, which you may not really have control over, right? So typically they are rated at something like 1% accuracy or 5% accuracy. Now that sounds like 1% sounds reasonable until you realize that if I was actually trying to count the number of clock cycles in order to run, let's say, a digital clock, right, a display corresponding to a clock, and I had a 1% error, then every minute I would be losing almost 1 second, losing or gaining almost 1 second. Every hour I would be losing or gaining almost 1 minute. So within a day I'm pretty much off by 15 minutes, right? And it's not really a viable way of running something like a clock, and that's with a 1% error. RC oscillators could potentially go up to a 5% error state and so on, which makes them not useful if you really care about how accurate your clocks are. So what do you do instead? There can be external crystal oscillators, right? Crystals are quartz crystals. They are literally made out of small pieces of quartz that have a behavior that their oscillation frequency is purely determined by the physical dimensions of the system, and they can be made extremely accurate and extremely stable, meaning that they don't really vary with temperature and environmental conditions. So you can get crystal oscillators that have very high accuracy and low drift or temperature sensitivity, but it is an external component. They are sufficiently common that you have sources of these readily available as chips that can be integrated into your design, but like I said, it's still an extra component that you need. Now this is fine. An oscillator, either RC or crystal, can give you one particular frequency, but as we already saw, I would like to have multiple clocks within my system. I don't want everything to operate at 48 megahertz. At the same time, I don't want everything to work at 1 megahertz either, right? I want to be able to generate different frequencies, and there are ways of doing that. One method is something called phase locked loops, which is a specific kind of circuit, which again is the details of how it works are out of scope of this course, but what phase locked loops, or PLLs as they are called, can do is frequency conversion. They can up as well as down convert. Primarily they are used for up conversion. Down conversion is actually easy. I'll get to that in a moment. But up conversion, taking a frequency of, let's say, 1 megahertz and converting it into 4 megahertz or 16 megahertz, how do you even do something of that sort, right? Because you are saying that I have a clock toggling at some slow speed, I want it to toggle faster than that, right? That's not in general a very easy, even conceptually. So it turns out that PLLs can do this. They have different kinds of oscillators and locking mechanisms by which they are able to generate multiples of your source frequency and lock onto that accurately. And that's great news, because for example, I could feed in something like a 4 megahertz crystal input, and from that, using a PLL, generate a 48 megahertz internally that can be used as the clock for my system, right? Now going in the other direction is called clock division, where I go from a high frequency down to a lower frequency. So for example, if I have a frequency f, all that I need to do really is have a very simple digital circuit that says on this edge, whenever there's a one clock edge over here, I make my output go high. Now on the next clock edge, I make the output go low. On the next clock edge, I make the output go high. On the next clock edge, I make it go low. Automatically, you can see that this second signal is half the frequency of the first one, right? What if I instead said on the first cycle make it high, skip the next cycle, wait for one more cycle and then make it go low, skip another cycle, make it go high, skip a cycle, make it go low. I've got f by 4, right? What if I do go up, skip 2 cycles, go low, skip 2 cycles, go high, I've got f by 6. So I'm not limited to powers of 2, I can get f by 6 and so on, but it's not as easy. F by 3 for example is not so straightforward, right? If I want to get a frequency of f by 3 and what's called a 50% duty cycle, that is it's on half the time, off half the time, it's not so straightforward to do it using this kind of clock division technique. But it can be done. Usually what is done is a combination of clock dividers and PLLs can be used in order to pretty much create a wide variety of different clock frequencies starting from simple inputs. And this picture over here is actually showing you the clock configuration settings that are available in the STM32 environment. Now this is something that we have this is a snapshot from the STM32 Cube IDE, right? So Cube Integrated Development Environment is the standard software environment that is provided by ST Micro for programming their microcontrollers. And if you create a project in that, pick any microcontroller you want and create a project with it, one of the options that you will see over there will be that you can actually choose the clocks that are available in the system, right? You can choose the clock sources, you can choose the frequencies, you can configure a lot of things just by sort of making certain selections in this GUI, right, the graphical interface. As you can see, there are a couple of things to be noted over here. One is that it already mentions there are two possibilities. One is that you can have an internal RC oscillator, right, the resistor capacitor oscillator, which it says is a frequency between 31 to 32 kilohertz. Ideally, it should have been exactly 32 kilohertz, but that's the point. It's saying that it's not all that accurate. It's between 31 to 32 kilohertz. On the other hand, you could give an external input of 32 kilohertz, and in fact, if you look at the number that's used, it's usually 32.768 kilohertz. Now, why this number? Because 32,768 is exactly 2 to the power of 15, which means that by doing clock division from this 32,768, by counting for 16,384 and then again inverting every 16,384 clock cycles, I will get an exact 1 hertz or 1 cycle per second tick out of this. So that's why crystals running at exactly this speed are common and can be used in order to provide the real-time clock of a system. Now the interesting thing is you can see that whatever clock is given over here is actually fed into a multiplexer, right? What does this multiplexer do? Basically what it's doing is it's saying that any one of these different clock sources, right, could be selected and fed into the RTC, which is in the range of kilohertz. In this case, by default, it's the internal clock that's being fed to the RTC. What are your other options? You have another 48 megahertz RC oscillator, right, where again you could have replaced it with an input frequency which is crystal driven, which could be between 4 to 48 megahertz. And once again, in the configuration tool, you can decide whether you want to take this or you want to take this. In this case, as you can see, it's connected up to the external oscillator out here, right? This one is the one that has been selected. That in turn goes through and comes out as a sys clock, your system clock of 48 megahertz. Now, there are these things called prescalers that keep coming up in multiple places out here. A prescaler is basically a form of divider, just like I showed in the previous picture, right? As you can see over here, this is sort of, you can think of it as a prescaler by a factor of 2. This is a prescaler or a divide by 4, right? Those prescalers can be used in order to derive clocks from a master clock, right? So, because of that, we can basically start with a high frequency and then prescale it down into the different lower frequencies. Now, looking over here, you can see that there are many different clock frequencies that are created. So, for example, it says that the overall power system gets 48 megahertz. The AHB bus, the AMBA high performance bus, which is a bus used by the ARM processors to communicate with what are usually considered high speed peripherals, right? Especially as there's something called the DMA, which we will talk about later, right? That's again running at the full 48 megahertz. The Cortex system timer, the timers are run at 48 megahertz. We'll be talking about those later. And the F clock in some sense is your core clock. That's the one at which your system is actually running. As you can see in this particular case, because of the settings that have been chosen over here, all of these clocks are the same. If you wanted to make them different, you could basically choose either the multiplexers or the prescalers at different levels and get different values out here. Now, why would you do that? If you knew that your application, for example, didn't need everything to run at 48 megahertz, certain things could be turned off or run at a lower speed, you can benefit in terms of power consumption by choosing your clocks properly. So, what are the implications of clocks in a microcontroller? The first, of course, is it determines the performance of the system, right? High speed means that you can perform more computations, but the flip side is it will consume more power. Now, there are certain interesting things that you can do with clocks. There is something called dynamic frequency scaling, which means that at runtime, I am able to change the clock, right? This picture that we saw over here is pretty much a fixed picture. It says that I have all of these clocks that are determined by a configuration setting before the system even starts. But there are ways, and depending on microcontrollers, not all of them may support it, but some of them do support mechanisms whereby you can actually change the frequency of operation at runtime, right? How this happens is that your PLLs can be configured to work differently, so they can actually change their frequency output. It usually takes a few maybe microseconds or so in order to switch from one frequency to another. So during that time you can't perform useful computations, but after that you will either be working at a lower speed or a higher speed than what you were doing before. Now, this is something that you are probably in fact used to in both your phones as well as your laptops. You might have encountered that when you are just sort of maybe reading a document or something, or browsing through a mostly static web page, your system is quite slow and cool, right? But then you turn on some video and then you're playing a game or something like that, the fans kick in, the overall system starts getting warmer. And why that is happening is that your CPU has basically responded to the fact that it has more load, more work to perform, kicked up the frequency at which it's operating, which means that it is more responsive. As far as you are concerned, you see it as, hey, I'm able to play a game smoothly, but the flip side is it's heating up, more power is being dissipated. Okay, so this can happen dynamically. The most computers today actually have mechanisms by which the software can control at what point to switch between different modes of operation. And apart from that, you can also choose many kinds of low power modes. So low power modes, typically there are multiple such modes in every microcontroller. The lowest power is usually what's called deep sleep. Of course, the lowest power is when the system is off, but something where you can actually get useful behavior is something called deep sleep, where for all practical purposes, the core system is cut off. The only thing that's really working is the real-time clock, right? What that means though is that there is still something that is providing power to that clock, right, providing a voltage supply. It draws a very minimal amount of current so that it can probably last even for months, possibly even for years on that real-time clock, and then suddenly wake up and do something useful. Right? So those of you who have seen things where there's one button cell that powers systems for like ages and ages, this is the kind of behavior that it has. It pretty much just goes into deep sleep until you press a button on the remote or something else which wakes it up and allows it to then respond to all the clicks that you are doing, send out infrared codes for turning on your television or something else like that, and then go back into deep sleep. Yeah. So all of this, essentially these implications come about because of the fact that you have multiple clocks, and it's a question of how well you are able to use them for the various kinds of functionalities that you need.